Hello and welcome, everyone. I might not be the first to wish you a Happy New Year, but I'd like to go ahead and do it anyway. Happy New Year. At the AAVSO, we are very excited to see what 2024 has in store. We already have some pretty big plans for this year, including furthering our collaboration with the Supernovae early warning system and migrating our website to a new framework. That one's kind of exciting. Should enable some even more advanced functionality. And of course, everyone here has their fingers crossed for T. Corona Borealis. Personally, one of the things which I am most excited for in this next year is our webinar series. We've put a lot of work into finding a top-notch slate of speakers who can discuss topics both usefully practical and fascinatingly theoretical. And this year, we have some opportunities for individual webinar sponsorships, which could be a great way to shine the spotlight on your astronomy-related business or project. If you're curious about one of those opportunities to sponsor a webinar, please just send an email to aavso@aavso.org, and we will be happy to chat. Now, for our new viewers, I would like to point out a couple of bonus features which you have access to since we're running Zoom in webinar mode today. First, if you take a look down at the bottom of your screen, you should see a Q&A button. If you click on that Q&A button, you can type in questions for the instructor. I would highly recommend that you do just that. After the presentation, we'll have an extended Q&A, and we will do our best to answer all of your questions. Also, please do note that it's a lot easier to find your questions when they're in the Q&A box instead of the chat box. So make sure you are typing them into the right spot. Another button, which you can see down at the bottom of your screen, is the CC or Show Captions button. When you click on that CC button, you can enable or disable Zoom's automatic closed captioning. It's not perfect, but it can be helpful. Next up, I would like to give a shout out to our other monthly webinar series, which is sponsored by the National Science Foundation. It is entirely in Spanish, including the title, which translates to The Science of the Sky for Beginners. Each webinar introduces basic science and astronomy concepts and provides opportunities for casual discussions between presenters and participants. It's totally free and aimed at the general public, age 12 and up. The very final broadcast in this series is scheduled for next Saturday, and it will be all about citizen science. Should be a good one. Please feel free to spread the word to your Spanish-speaking friends and colleagues. It is not necessary to have seen all of the previous webinars to enjoy this one. And now, back to the webinar at hand. Today's webinar is sponsored by Voice Astro. We would like to take a moment to thank and acknowledge them for their generous support. The Voice Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, such as the Journal of the AAVSO. Please check out their webpage to learn more about their work. All right. So if you have been watching any of our recent webinars, today's presenter is likely to be a familiar face to you. He's a newly elected member of the AAVSO's board, as well as the co-leader of the cataclysmic variables section and an experienced photometrist. About 20 years ago now, he helped found the Sonoito Research Observatory, and more recently, he introduced the Madrona Peak Observatory into AAVSONet, which means that he is directly responsible for two of the AAVSO's largest remote telescopes. On top of all of that, he's a longtime member of the Center for Backyard Astrophysics and the person who introduced me to variable stars. I have a particularly vivid memory of stopping by his observatory one night while he was recording a precision photometry of a CV for the CBA and listening as he explained what a cataclysmic variable was. That night taught me two things. One, there is still so much out there to learn. And two, Walt really knows what he's talking about. So I am very excited to be able to introduce today's talented instructor, photometrist extraordinaire, Walt Cooney. Welcome, Walt. We're glad to have you here.
Well, thanks, Lauren. I don't know if I can live up to all of that, but I will certainly try. And by the way, too, I have actually asked someone else to join me today. Ken Menzies is on board. He's a longtime AAVSO participant, has done many things in the organization. And one of the things he does is he teaches our choice course on VPhoto, which is the photometry tool that the AAVSO supplies to members. And Ken is the expert. I use that tool. It's a great tool. I use it a lot, but Ken knows much more about it than I do. So I have him on board to help us answer your questions when they're outside of my depth there. So let me share my screen. Oops. Okay. Working?
Looks great.
Okay, fantastic. Thanks, Lauren. Okay, so this is an introductory photometry course webinar. I will say that we'll spend maybe 45 minutes in discussion here for the talk, and then it could easily go on another 30 or 40 hours, and there would still be plenty more to learn. But I hope this is a good introduction for you to give you a good starting point. And let's start with this. This is R.S. Ophiuchi, and I'm just assuming that some of you can tell which one of these is the recurrent nova R.S. Ophiuchi. This picture where it's bright was a picture in 2021 when this recurrent nova got up to about fifth magnitude. The second picture where it's faint, I think, is from 1989, and it is from the Palomar Auschwitz-Schmidt telescope and goes much, much deeper. And so that helps you give some perspective on how much brighter this recurrent nova went when it went off. And I'll put in a quick plug that we're thinking, we believe T-Core Bohr is going to do this and get all the way to second magnitude sometime in about the next 6 months. So keep your eye out for that. But anyhow, this is a neat picture, a neat animation. And but there's one thing that you can't tell from it is, well, it's a lot brighter, and we can do better than that. And this is what we really want to do. So this is the light curve for RS Ophiuchi from the AAVSO webpage from 2021. And here it is where it normally runs about 11th magnitude. And then when it went nova, several folks were able to catch it on the way up, which is a fantastic thing to do. And then it peaked here at about 4.5, 5. And then over the course of weeks and months, it slowly faded away. And so these are the kind of measurements that we do as part of the ABSO, and these are the kind of measurements that really help out science, astronomy, trying to understand what's happening with all of these amazing variable stars. So a couple of assumptions to start with for our webinar here. They're not huge assumptions. They're just that you have taken astronomical pictures before, whether that's with a CCD, a CMOS chip, or with a DSLR, which would be a CMOS chip as well. And then you also know how to calibrate an image. And so with a CCD, that's going to involve bias, darks, and flats generally. With the CMOS chip, it'll be darks and flats. And in the background here, we have a picture from Jeff Lepp, who is an amateur astronomer here in the Houston area. And he's the president of the Fort Bend Astronomy Club and a member of the Houston Astronomical Society. And quite the spectacular picture of M5. And I will say, your pictures don't have to be this spectacular. This is a beautiful picture, but photometry is quite forgiving when it comes to beauty. Our purpose is to measure brightness and see how stars are moving around, and so we can sacrifice some of the pretty pictures to get to the science. Okay, so how do we measure the brightness of a star? The main tool that we use is aperture photometry. It's really pretty straightforward. You use software, and you should be able to see my mouse, to be able to put this bullseye over a star in your image. And this first area here is the measurement aperture around the star. And then we have a gap. And then between these two outer circles is where we measure the brightness of the sky background itself. And so we call that the sky annulus. And the brightness of a star, in simplistic terms, is really just a measurement of the pixel counts inside the measurement aperture minus the pixel counts in the sky aperture. And of course, there's some math involved to make the geometry work out properly. You know, the number of pixels here and the number of pixels in this outer annulus aren't necessarily the same. And so there's a little bit of math behind the scenes. But fundamentally, that's what we're doing, is we are measuring the amount of flux, the amount of energy, the amount of light in this aperture around the star. And we're getting to just the star's light by subtracting the background sky brightness with the sky annulus. So the output of this isn't the magnitude that you think of when you say, you know, Polaris is a second magnitude star. This is actually an instrumental magnitude. It hasn't been put on a direct scale like our visual magnitude scale that we think of, at least not at this point. And so to do that, we use differential photometry, and we have two stars in the field that we'll be using. One of these will be the comparison star, and that's a star with known brightness from a catalog. And then we have our target star. And when you use the software to determine the instrumental magnitude of the comp star, the comparison star, and the difference with the target star, the difference in brightness, now knowing this real brightness, real magnitude, you can go back and determine what this magnitude is on the standard magnitude scale that we use. And so here's the semi-equations in terms of instrumental magnitudes. And we're actually not quite done yet, because we need to check our work. We need to make sure that we have a reasonable answer to what the target star magnitude is. And so we'll throw in a third measurement aperture of a check star. And this will be another star with a known catalog magnitude. And we'll calculate the variable star magnitude, we'll calculate the check star magnitude, and we'll see how our measurement of the check star compares to the known catalog magnitude for that star. Now what you'll find is the answer is not going to be perfect. If this star is 10.10 and your measurement of it is 10.15, that's within reason, and there are lots of reasons why you won't measure things perfectly. There is just a little bit of statistics involved in all of this, and sources of noise, and how your specific telescope and camera function together determine light of colored stars. But so the target here is to just prove that you're quite close to what this check star magnitude is. And then you'll have confidence that you have a good target star magnitude, a good variable star measurement. So let's talk through a few of the things that go into making these measurements. part of doing a good job with this. Aperture sizes is one. So if we look at this, I've laid down some aperture sizes here, different diameters. Your software will allow you to choose those. And just looking at it, what I've done seems reasonable to the eyeball. We can actually do just a little bit better than the eyeball, though. We have some recommendations on what these measurement apertures should be. And in particular, the measurement aperture should be generally about 1.5 times the full width half max of the star image. Now, I have also assumed that full width half max is something that you're familiar with. It's effectively a measurement of the size of the star image on your photograph. And without going into all the details of where a number like this comes from, 1.5 times your full width half max gives you a pretty good optimum for an accurate measurement with modest noise. Now, it is not a hard and fast rule, and you can squeeze this. I have used apertures as small as 1 times the full width half max, or even smaller in the past in very particular situations. There are some risks and some issues with doing that, especially if you push it really hard. A particular place where you'll often think about it is where you have a tight neighbor. So you have 2 stars very close, and you want to measure one of those, and you don't want your measurement aperture to extend over both stars potentially. And so you'll have to squeeze one measurement aperture, or your measurement aperture, down so it only encompasses the star of interest. The problem with this is that you potentially sacrifice some accuracy. You can improve your precision, but only to a point. And it's a big topic. I think we'll just leave it at that. Maybe there'll be some questions we can talk about after the slideshow. The other thing I'll note too, there are lots of rules of thumb on the size of the gap between the measurement aperture and the sky annulus, and then the width of the sky annulus itself. And I didn't even put those in here. Honestly, I think you can use pretty good judgment there. Your sky annulus should be thick enough that it incorporates a lot of pixels, and so you get good statistics in your measurement. And most importantly, you should try to avoid having other stars in your sky annulus as much as possible. Now that's not absolutely true, and it's also not absolutely possible all the time. It's not uncommon that there are some faint stars, and for instance, if you're able to find a place where your sky annulus doesn't include any faint stars for your variable star, well, it does for the comp star or the check star and vice versa. And that's okay. Some contamination of faint stars can be handled effectively by the software that you use. It uses different methods to throw out outlying pixels that are clearly too bright for true background measurements. And that said, those methods are only so powerful. And if you really do have a fairly bright star in your sky annulus, you're very likely impacting your measurement. And so you try to avoid that. Filters. There are a lot of questions about filters, and a lot of answers. The simplest filter is unfiltered. and that would be just your telescope and no piece of glass whatsoever in your filter wheel, so that you shoot directly through the filter wheel, or you don't have a filter wheel at all. That would truly be unfiltered. There are also filters called clear and luminance. And, the clear filter is defined differently by different people and by different companies. With some companies, when they sell you a filter, you'll find out that for them that meant it blocks ultraviolet light, while there are also clear filters sold out there that will block infrared light instead. But a luminance filter is fairly well defined. A luminance filter is something used for color photography. It blocks both the ultraviolet and the IR. And the reason it does that is because you want an RGB, a red, green, blue picture. And if there are ultraviolet and infrared photons coming into your picture, then that is really altering your color balance. And the easiest way to improve that in photography and pre-picture work is to use a luminance filter to take out UV and IR. As far as photometry, though, for variable stars, there are really two clear use cases for unfiltered. One of those is where you're trying to understand the time behavior of a star that's varying at very short time scales. And so the example that was mentioned by Lauren of cataclysmic variables is where this is very often used. Cataclysmic variables vary on all time scales: seconds, minutes, hours, days, years. And part of what we want to understand about cataclysmic variables includes what's happening at all of these time scales. And so you would potentially shoot a 5-hour time series on a particular variable, and you would want to get an image of it as quickly with as small a time difference between images as you can. And so in that case, where you're trying to do high cadence, you'll give up the fact that you're not going to be getting color information uh, just because you're trying to see what's happening quickly, and you'll just make that sacrifice. The other place where you would use an unfiltered or a clear or a luminance filter to measure a variable star is when it's very faint. And if you're using a color filter, you really can't get to it. You can easily go a couple of magnitudes fainter without a filter, depending on the particular star and the particulars of your system. And so if you're trying to get a measurement of a star that's 19th magnitude with your 6-inch telescope, it behooves you potentially to take the filter out and gather as many photons as you can. And so in that case, your data would go into the AVSO as what we call CV data. You would use reference star magnitudes in a V-band color and base everything on V-band. So for instance, Polaris second magnitude, you would use that if that were one of your comp stars. But you're not actually using the V or visual filter. You're using an unfiltered system. And so the AAVSO has a special notation for that called CV, or clear with a V 0 point is a more wordy way to put that. So, but there are other filters. Well, let me back up. If you're not using unfiltered, if you want to do color photometry, which is very highly encouraged, then you would use filters that correspond to some of the standard filter colors that have been used by astronomers for years. The most famous system is called the Johnson-Cousins system. and it's UBV, RC, and IC. And so that is ultraviolet, blue, V, meaning visual, although it's effectively green, but it's called V for visual, RC. And so the C is actually standing in for cousins, same red, infrared, RC, IC. So the UBV filters, the UBV colors are the original Johnson colors, but an astronomer named Cousins came in later and adjusted the R and the I for some good scientific reasons. And so typically those are used together, UBV of Johnson and RC and IC of Cousins, and that's what we would call UBV or I. And I have to mention one of the most important things about this system is the system. I think Johnson Cousins was late 50s and early 60s, if I remember right, when this was first um, started put in use. But there were just a few stars that were selected as the standards for that. And when you're doing photometry, you need to be able to use stars that are close by for the comp star work. And so Arlo Landolt, Dr. Arlo Landolt, who finished his career at LSU, originally got his degree and did a huge amount of work at Indiana University. Dr. Landolt, starting in the 60s, spent 50 years accurately measuring the colors and brightnesses of non-changing stars all over the sky. And it was just an incredible amount of work and an incredible contribution to the field of astronomy. And you have to hand it to him, because if you would tell most astronomers that your goal is to measure stars that don't change, they wouldn't be terribly interested in that project themselves. But Dr. Landolt was the one who went out there and did that, and his work is really kind of legendary in astronomy as a result. So anyhow, so all of the standard stars that we now use, the most important set of standards are Arlo's original standard stars. Okay, so there are other color filter opportunities though too, that especially this one, the Sloan set, that is now coming more into use. And this is a set of filters that correspond to the ones used in the Sloan Digital Sky Survey, if you're familiar with that. It's a somewhat different definition of colors. In particular, G, that they call it here, they're green, is actually a strong mix of B and V. It spans most of B and V, and for various astrophysical reasons. And it's usually denoted as U prime, G prime, R prime, I prime, and Z prime. And that gives software trouble when you have those kinds of notations, those kinds of characters. And so for AAVSO data, if you're going to submit work with those color filters, then you would instead say Sloan U, Sloan G, Sloan R, Sloan I, Sloan Z. So SU, SG, SR, SI, and SZ. And that way you don't have to use the prime notation here. And then I'll mention one other color band that hasn't been used very much at the AAVSO until really just recently. We've started using it substantially. It's H alpha, the same H alpha that you will use for narrowband photography. And for certain stars, there's a lot going on in H alpha. And rather than using spectroscopy, which of course would give you the most information, There's still information where you use your H-alpha filter to measure the brightness of a variable star. And there aren't a lot of comparison star magnitudes out there for H-alpha. There's really no true standard system. There have been a number that have been proposed over the years, but none of them have been used broadly. And so the typical thing to do when you're measuring the H-alpha magnitude of a star is, for your comparison star, use its R cousins magnitude. And then when you report your photometry, you will call the variable star an H-alpha or HA measurement. And the particular campaign that has been using this H-alpha measurement is for young stellar object, AB Aurigae, where they are looking at the planetary system that appears to be forming around this star. And in this case, there's a lot happening in H-alpha. And while the professionals are using the Hubble Space Telescope to look at this, and they're doing spectroscopy with big professional telescopes on mountains, us amateurs are helping them out using H-alpha photometry and submitting that to the AVSO. Something to beware of in photometry: saturation. So if you have a standard CCD camera, typically a 16-bit camera will get up to about 64,000 counts for any one pixel. And if you do photometry where a star has reached the maximum counts, I'm afraid it's going to be bad data, because what's also happening at that point is the pixels have lost the count on additional photons that hit after that 64,000 number. And in truth, it's even a little different from that, because most CCDs, CMOS chips, etc., they actually, even before they reach saturation, their response will become nonlinear. And so if, for instance, your particular chip, every time one photon hits it, you get 1 pixel count. When things start going nonlinear, maybe it means your chip, your pixel needs 2 photons to go up 1 pixel count. And in that case, all of a sudden, it's also going to skew your photometry. And so this graph here is a measurement of a particular chip, the Kodak 16803, with an anti-blooming sensor. This has been a very popular chip, but it's a huge chip, so great wide field stuff, been used in photography, astrophotography for years. And this was a linearity test done on this chip. And so all they have measured here is when you've got a source of light exposing a pixel, a constant source of light, over the course of a certain amount of time, the ADU count, the pixel counts for each pixel, goes up linearly until, in the case of this chip, this is about 65,000. And so it doesn't lean over and go nonlinear until it's pretty much fully exposed, fully saturated. And it's one of the nice things about this chip, to tell you the truth, is that it goes to such a great depth before it finally starts giving you bad photometry. It's not uncommon for other CCD or CMOS chips to start curving off maybe 60,000, maybe 55,000. You can measure this yourself to understand your camera, and that's ideal. I would also say, though, that for many chips that are out there. That work has been done. You can Google it and you can find a graph something like this for your chip already and find out at about how many pixel counts your graph starts going nonlinear. If you really don't know an answer to that, if you can't Google it and you haven't done the work, then I would consider, say, 45,000 or 50,000 as a max ADU count on a 16-bit chip. And so that's another subtlety about this is I've been talking about the 16-bit chips that are so common in the CCD world. In the CMOS world, there are quite a few cameras out there that are only 12 or 14-bit, even as low as 8-bit. And in that case, the counts never get to 64,000. You might only get to, say, 16,000 as your max possible count for a 12-bit chip. And on top of that, what makes CMOS chips a little more difficult to use properly is, well, at least for CCD chips, the linearity, the response of the chip to photons, which is the gain of the chip, is normally set and locked in for that chip. And so when you bought a CCD camera, you didn't have the option to change that gain. That's not the case for CMOS chips. They give you that extra knob to turn. And so you can change your gain all the way from 0 to maybe several thousand. And that's a great freedom to be able to do that. It also throws curveballs in that it's harder to know what your limits are for linearity and for saturation. And it also makes it harder to go Google it and find an answer. There are answers out there. A lot of amateurs have done work with their cameras and then told everybody what they found. And you really do need to understand in that case where your camera reaches saturation and or where it starts going significantly nonlinear. So I'll just leave that there. That's a bit of a that subject can bear lots of conversation. Okay, well, back to the actual measuring. I talked about we have a comp star, a comparison star, that you measure your variable against. And so where do you get the magnitude of that comparison star? And in the AAVSO world, they make it really easy for you. Over the last 100 and something years, the AAVSO has done massive amounts of work identifying good comparison stars for variables. And over here on the right, you can see a chart for T-core bore, if you recognize the name. And this is T-core bore, the little circle and the crosshairs here. And then these are recommended comparison stars to use for your photometry or to use for visual work if you want to do a visual estimate of this star. And this 99 here, that's not a catalog number. That's actually the magnitude of the star in with the decimal place omitted, because if you were to put the decimal places on the chart, there's some potential they could be confused as stars. And so all of these numbers that you see here on the chart are magnitudes with the decimal omitted. And what you'll find is comp stars have been given for the full range over which that star would normally be expected to range. Now for T-core bore, since it'll get all the way up to second magnitude, when it gets that bright, you would have to generate a chart with a larger field of view And when you do that, I think it brings this star in as a comparison star. And if I remember right, that star is something like 4.4. But you have to get far enough out in your chart so that you can see some of the brighter ones. But if you're doing photometry of this, when it's hovering around 10th or 11th magnitude, your field of view might be something like this rectangle, depending on your system. And then it would include several of these comparison stars for you to use. Now, the one thing I would say is there are lots of other places where you can get star magnitude measurements. There are some tremendous catalogs out there. It would be it's the topic of a really great seminar to go through some of the tremendous catalogs that are out there. And what I would really recommend to you though is to not use those. And the reason I recommend that is because the comp stars that have been selected on these charts by the AVSO are ones where we've already confirmed that it's a constant star. There's been no evidence of variability. They choose star magnitudes to be consistent across catalogs. There's an awful lot of work that goes into properly choosing a comparison star. And then on top of that, those comparison star magnitudes are documented. And so 50 years from now, when people will be using your data and they need to understand a little bit more about the specifics, we've got the specifics already logged in the AAVSO world for you. And those future researchers aren't chasing a moving target with no ability to hit it. Now, on occasion, you'll be working a star and you need a comparison star, and there's not one that's available to you, maybe because of the size of your frame or the brightness that this star happens to be at, or for whatever reason. And I would just ask that you have a little bit of patience, because the AAVSO sequence team, which generates comp stars, is still at work. And typically, if you send a request to those folks, they'll get you a comp star within about 24 hours. Just tell them what variable star and what kind of magnitude you're looking for. And there are a couple of ways to do that on the web. You can ask for a sequence, a comparison star sequence for a variable star that has never been worked before with this link here. Or if you just need one extra comp star on a particular one, say on this particular T-core board, you need a 18th magnitude comp star for whatever reason, then you would just add that request on this web page, and almost always within 24 hours, 48 hours max, they'll get back to you with an answer, and then you can submit your work. And again, I'll emphasize, if you don't use comp stars that are designated AVSO comp stars, really your measurements are of somewhat less value. And while there are times where you have to do it, and we won't go into those times, I pretty strongly recommend against it. Okay, so I mentioned software kind of as this broad general, the software does things. Well, so what software can we actually use? The AAVSO has a really terrific online software tool. It's called VPhoT, Variable Star Photometry, and it is online, web-based. You do need to be a member to use it, but it's very powerful. I use it quite a bit, and we'll talk a little bit more about it in a minute. But there are other options, and I use some of these as well, depending on what I'm doing. AIP4Win is a very popular program. It's actually written by Richard Berry, who is the current president of the AAVSO. And at one time, you may know he was the editor of Astronomy magazine. And this used to come with his book. And now he has made AIP4Win, the program, as freeware available to anyone, and it's a terrific program. A lot of people use it. I'll put in a plug also for Less V Photometry. This is written by a Belgian man, Pierre Dupontier, and it is a terrific piece of software as well. It has some capabilities that some of the other packages don't have, that lend itself to the kind of work you may be doing. It's also freeware, although I will say Pierre gives you the opportunity to donate if you would like. And anyhow, and then there's commercial packages. Myra is excellent. Maxim is excellent too and very well known. A lot of people use it. AIJ is one that is used heavily for exoplanet photometry, and the AVSO is very heavily into exoplanet work. Then there is a professional tool, IRAF, and it was the gold standard for many years. It's incredibly powerful. Many astronomers over many years worked to develop IRAF and make it the powerful package that it is. But you've probably heard of user-friendly software, and I think of IRAF as actively user-hostile software. It's quite challenging to use. I have actually used it, but it was quite the effort, and I hope not to ever have to go back and relearn it for any particular task. There are some other options. PyRAF is a Python wrapper around the IRAF that simplifies the IRAF work a little bit. And then PhotoUtils is a relatively new Python package that you can do both aperture and PSF photometry. We'll talk about that in a second. And there's a lot more software options. These are some of the prominent ones I wanted to go ahead and list. Okay, VPhoto. This is a screenshot where I am actually measuring the brightness of this star right here, V838 Monoceros. And this is the variable star, this is the comparison star, and this is the check star. It's 12.0 nominally. The comparison star is 12.3 nominally. And this is some information over here. V838 Mon, the signal to noise in this, I think this was either a red or an infrared image. Signal to noise is all the way up to 600 here. The check star signal to noise is 176, and the comp star signal to noise is 203. The full width half max is measured for you. And Ken, are you out there? Can I ask you a question?
Yeah.
It doesn't actually, I have not ever found it in the documentation. It's not here online. I presume this is arc seconds, full width half max, right?
No, actually, that's pixels.
Is it pixels? Okay.
And the thing to remember, for everybody to remember, that these are individual ones, but the average is really what you should be concerned about. You will use one aperture based on full width half magnitude for all of the stars on the chart, on the picture. And it's about 3 in this case, as you can see.
Okay. Well, thanks. Thanks, Ken. I appreciate it. So generally, when you're comparing full width half max between different telescopes, different people, different work, you'll want to convert that to arc seconds so that it's comparable, of course, since of course pixels are dependent on your particular system. In this case, thanks, Ken, so it's actually just pixels when you're doing the work in VPhoto. So this isn't a course on VPhoto. There's a lot of great documentation and a lot of the manual that's very helpful. And of course, I mentioned Ken's course on VPhoto that he will offer again either this October or November. So we won't go into it deeply, but I will show you a couple of other of the capabilities of VPhoto just to give you a feel for it. Like I say, incredibly powerful. This is one of the neat things it does. I have already with this image, as a matter of fact, I've blown this out a little, zoomed out a little bit. You can see these are my 3 original ones here. And I have added via vPhoto and the AVSO database, I've added every other identified variable star in this field, just automatically, click of a couple of buttons. I've also added every AAVSO comp star that I could choose to use. And they're all listed here. But before I sell this too strongly, I do want to tell you that the wrong thing to do would be to now try to input photometry, to try to submit photometry for every variable that's seen here. First off, the ones listed here that have the little red asterisk next to them, those stars aren't even in the AAVSO database, and so you can't submit data on them. Not every star in the sky is on the AAVSO database. And then on top of that, even if it is in the AAVSO database, like this one here, and I don't know anything about this particular star. In this case, the signal to noise was about 60, so it got a decent measurement of it. But that may be a star that only varies by 3/100ths of a magnitude. And in that case, that there may not be much value in your submitting that photometry. In any case, you really need to understand a little bit about the star and the value of the photometry you would submit before you just blindly submit numbers and hope that's helpful. And maybe there'll be some questions about that. We can talk more about that afterwards. Okay, another difficult bit, neighbors and crowded fields. It's not uncommon that we can't draw that nice aperture around the variable star that we want to measure without having a neighboring star intruding. And of course, when you're in the deep Milky Way, trying to do photometry of variable stars, then it's very common to have very tightly packed stars, and it makes photometry a little bit more complex. And there's a couple of, actually, I guess I'd say there's 3 ways that you can do that. You can draw a bigger aperture that includes both of the stars in your measurement. And you can use a spreadsheet that was put together by Lou Cook, a longtime amateur astronomer and AAVSO a contributor. He calls it his nemesis Excel sheet because the neighboring star was the nemesis to getting good photometry. And if you enter your measurements, your measurement of the combined star, and then you know some information about the neighbor star, including what its actual catalog magnitude is, then with Lou's spreadsheet, he will subtract the fluxes, do everything in with the correct math, the correct theory, and he'll allow you to subtract out and get specifically the measurement of the variable star only. And so that's very powerful. It's actually quite easy to use. It's just a few inputs, really. Alternatively, if you're looking at time sequence work and you just want to see how a cataclysmic variable changes over time, in those cases and some others, it would be acceptable to submit your measurement of both stars together. But I would put a note for your measurement that both stars are included in your measurement, and so a future researcher will understand that. And then the third way to do it, and this is a really powerful way to do it, is where you actually, let's go down here and look in the corner. This is off a real image. This is one of my images. This is the X and the Y of the photograph, but then in the z-axis those are the pixel values for that star. And so you see, when you look at it this way, that a star is kind of a Gaussian mountain, a Gaussian hump in your star image, and that's your point spread function of your star. And so PSF photometry will actually go to separated stars, lone stars in the image like this one is, and it will model the Gaussian, the shape of your star. And so it can then use that model to look at the Gaussian where you have both the star of interest plus the neighboring star, and it will use the model to separate those into two separate Gaussians, and you can actually deconvolve the two stars. You can get the measurement of your variable star by itself that way. Like I said, very, very powerful. It's available in IRAF, and that was the one time in my life that I used IRAF because I was doing a project like this, and that's why I would call IRAF actively user hostile. But there's a new option. There's also something called Photo Utils that does have PSF capability, although I haven't used it and can't tell you too much about it. So I guess there's even a fourth recommendation on stars like this. Pick a different star. These are hard, especially if you're just starting out. This is a lot of complexity. There are an awful lot of lone stars that don't have this complexity that could really use your help, really use your work. And so I would work with those until you're ready to jump into something like this. Okay, another thing to talk about is binning. This is particularly important in the CMOS world, where the pixels are becoming so tiny. You know, the 2.4 micron pixel is a common pixel size now. And while in the CCD world, the pixel size of 12 or 13 microns was not uncommon, and there were some with pixel sizes as high as 24 microns. And so just a few pixels could cover your star. With CMOS work, you can end up where your star has literally 60, 80, 100 pixels with starlight falling on it, and really that has some downsides. And so seeing is how you make a judgment on binning. And so a professional observatory on a good mounting, sorry, I think it doesn't have a G after that in real life. A professional observatory will often have 1 arc second seeing, or maybe even what they'll call sub arc second seeing. And so that means the full width half max of their stars on their images are 1 arc second, which is fantastic. A really good amateur site might have seeing of 1.5 arc seconds. A pretty good amateur site, 2 to 3 arc seconds, and a typical amateur site might be 2.5 to 4 arc seconds. And this is something that's very easy to measure with all of the software we just talked about. And you'll see these you're seeing move around, as a matter of fact, over the course of the night, especially day to day as the weather changes. And so for binning, you want to do some optimization there. And so, for instance, if you had a star image with a full width half max of, say, 5 arc seconds, then you would not want pixels that are larger than, say, 2.5 arc seconds, because you're undersampling. You're catching starlight in just a few pixels, and pixels are square and star images are round, and so that's maybe the easiest way to see that you're starting to impact your measurements with that. And so in some, again, rules of thumb, you would want, if you're less than 2 pixels, if your pixel size corresponds to 2 pixels per full width half max, then you're undersampling and you're impacting your photometry. Potentially, you would want that to be more like 3 or 4 pixels. And oversampling is really preferred over undersampling if you have to pick one. But either way, you can adjust all of these things with binning. So if you have these super small pixels, you can bin them so 4 small pixels are added together to make 1 square superpixel. And that would be 2 by 2 binning. 3 by 3 binning would be 9 total individual pixels that make 1 superpixel. And doing that can improve your photometry. It can also help you that it will reduce the read noise, which is an impact on your accuracy. But I will say that has a much bigger effect on CCDs than it does on the new CMOS chips that people are using. So again, much more could be said. I hope that gives you some flavor of what to think about when you're looking at binning. I think I say it on a different slide too, so I'll just go back to this. The critical mistake that you can make with binning is that one of those pixels, let's say you're 2 by 2 binning, and so you have 4 little pixels being made into 1 superpixel. If 1 or 2 of those individual pixels is saturated, potentially when they form the superpixel, it won't look saturated anymore because the 2 other pixels of the 4 are significantly enough under saturation. Now it looks like the whole superpixel is not saturated. In truth, if one individual pixel is saturated, then the whole superpixel is not good. So a little bit more about that later. Color transformation. This is a big subject, and you know, I think actually in the interest of time, I'm just going to skip through this. It's the way that you put your work on the standard system like UV, V, RC, IC. It's what you would do if you had 2 filters. Let's say you were using a B filter and a V filter. Then you could do color transformation to improve your measurements. One more slide on that. VPhoto has really the best algorithms for helping you with this. It makes it amazingly simple and straightforward. And anytime I do any kind of transformation, I used VPhoto specifically and some tools that go with it. Okay, uncertainty, aka error. Software is usually going to report this as 1 over the signal to noise. So if your star has a signal to noise of about 100, then it's going to tell you that your error for that measurement is about 0.01 magnitudes. And unfortunately, that's just not really quite right. That underestimates it. It's the simplest and most straightforward way to get an approximate value for error, but it's not the best way, or at least it's not it doesn't get all of the sources of error by doing that. In truth, it's better to take multiple measurements and then see what the scatter is yourself. As a matter of fact, you can enter those several measurements into the AAVSO database, and that way you give a future researcher clear information about the kind of scatter that was in your data. That can still be an underestimate, though, because unless you have done color transformation, you aren't fully on the same standards set of magnitudes that Arlo Landolt um, generated so much work, so much data for. So all in all, though, I will say that most of the data in the AVSO database has an error that's based on 1/, signal to noise, and it's an underestimate, but at least it's something, and it's important to at least have that. DSLR photometry, this is not my expertise. I will refer you, and I understand Barbara's actually on the webinar today. I'll refer you to her video from, I think, 2 years ago. It's on the AAVSO HQ YouTube channel, where she gives a webinar on DSLR photometry, very helpful. I mentioned a couple of points. You still have to calibrate your images with darks and flats. You may need to defocus a little bit so that you're sure that you're not undersampling your stars. Your camera has to be able to save data in the raw format. That's what's useful to the astronomy software. You'll actually separate the color channels from your image. Red, green, blue, you'll get effectively an R image, a G image, and a B image off of your 3-color image, tricolor image. You'll debayer the pixel map. And by the way, software does this, but these are the overarching, this is the look at what it's doing. You'll debayer the pixel map. And so you'll effectively, typical Bayer pattern has 2 green pixels for every B and every R. And so to get everything normalized and working together properly, when you debayer, it's going to take those 2 green measurements and it will average them to a single measurement and use that as a single pixel, for instance. In DSLR work, you will, rather than RG and B, for the AAVSO database, to make sure that it's understood that those are RGB, DSLR, colors, instead of B, it's TB, TG, and TR for those color codes. And so that really means tricolor blue, tricolor green, and tricolor red. And then again, I'll point you to the really, really helpful DSLR photometry manual that's available on the AVSO website and Dr. Harris's YouTube channel or YouTube presentation from a couple of years ago. Tricks of the trade. I'll try to go through this quickly. This is going just a little bit more into depth to a few things to pass on to you. One that I really want to emphasize is the quality of your data is your good name. And what I mean by that is if I'm working on a particular star and I'm trying to understand what's going on in its light curve, if I see the data is from Ken Menzies, for instance, I will think, well, this is good data. I can hang my hat on it. Now, that's not to say Ken and everybody else in the whole world doesn't make mistakes. But by and large, 99% of the time, this is good data. I have confidence in it. And I will say that not everybody takes enough trouble to make sure that their data is good. And the risk there is if your data is sometimes not so great, then people throw out a hand entirely. It's not to say You have to be perfect. We all get better over time. Really, my point is that quality needs to be important to you. And if that's the case, I think you'll do a good job and you'll have good data, and people will recognize that. Part of that is look at your images, look at your data. It is too easy with these amazing programs out there to throw the images into the software and see numbers spitting out and think, gosh, how about that? And submit it. And there are an awful lot of things that can go wrong in these programs. You really need to take some look at what's going on, look at your images, look at your data, make sure it seems reasonable. After you've submitted to the AAVSO, go look at how it blends in with the rest of the data people have submitted. Does yours look reasonable? What reasonable is depends on what kind of things that particular star does. But, for instance, there was a star I was working a few years ago, and someone had inputted data to say that for some long period of time, that star was 28th magnitude. And I'm quite sure that they were not using the Hubble Space Telescope for their work, because that's one of the few things in astronomy that could actually measure something at 28th magnitude. And so it was mistaken data. We make mistakes. You contact the folks, you let them know, hey, looks like maybe this is a mistake. The correct response from those people is, oh, shoot, thank you for pointing it out. Let me go fix that. So do that up front with your own data. A couple other gotchas, a reason to look at your images. The centering of a star in the aperture is done automatically. Sometimes it's not perfect. Take a look, just make sure that seems reasonable. Sometimes the software will actually jump away from the star you're measuring and measure a nearby star, a nearby constant star instead. Happens a lot. There's a fair bit of data in the AVSO database of neighboring comp stars as opposed to the actual variable. Do great calibration, understand how to do darks and flats, do that as best you can. Quality over quantity. You can stack multiple images of a faint star to get a better measurement. And that's particularly helpful with 12-bit cameras where saturation comes so fast. And so you can build a better image by stacking shorter images. If you're using CMOS, you have to use the same gain and offset parameters for your data images and your calibration images and everything else. And that's a real gotcha that's easy to fall into. Let's see, I mentioned that match calibrations. Refresh your darks and flats. Darks may be good for months. Flats, maybe just days, weeks, maybe months. It really just depends on how dusty your area is and how stable your OTA is. You really want to use exposures no shorter than 5 seconds, or then stack shorter exposures to get to more than 5 seconds of exposure because of twinkling. It's called scintillation noise, but all that twinkling that we see in our atmosphere is noise to photometry. And so if your image is, say, 5 seconds, maybe 10 seconds or longer, you average out that scintillation, that twinkling noise, and you get a better measurement. And then the one last thing I'll point out is scattered light in the optical system. If the moon is shining down your tube and you can see reflections, that can certainly impact your photometry. And as you get to more and more accurate work, you might find yourself chasing down the last little bit of scattered light in your optical system to help. Okay, you'll never stop learning how to do better photometry. I've been doing it for 20 years. I learn something constantly. I'm always getting a little better at it at least. Keep learning. Ask for help. The people who do this enjoy it, would love to help you out. They want you to be able to do good work. So ask for that help. We've got the forums on the AVSO website, and we have mentors available to work with you specifically. You can email email the AVSO, and we'll get somebody in touch with you to help you out. Resources, lots of great ones. These are on the AVSO website: the photometry manual, DSLR manual, Ken's course, Dennis Conti's course that works with AIJ for exoplanet work. Arnie Hendon did a course some years ago over several days that is the course for amateurs on how to do great photometry, and you can buy the access to that, streaming access to that through the AVSO. I go back and watch it still on occasion, different parts of it, and still learn things that I can do better from that. And then the HQ YouTube has lots of webinars over many subjects that are free and open to you to learn from. And thank you very much. I appreciate you holding with me. I talked a little longer than I had intended. But anyhow, open for questions.
Thank you so much, Walt. That was an excellent introduction. Awesome. Okay, so we have had a really huge amount of questions come in. This is going to be a fun Q&A. So I've broken things down kind of by topic, and let's start with this really excellent question from Jamie Jenkins, who asked if you could please explain the difference between accuracy and precision.
Okay, yeah, that's a good question. So accuracy is the overarching number, and so if you know that you have 10 oranges, then the accurate count for oranges would be 10. But a very, very high precision count for your number of oranges might be 11, and you count 11 50 times in a row. You have great precision, you have great consistency in your measurement. Your accuracy is off. The real number is 10. And actually there's a place for both of those. In the perfect world, we want both. We want 50 straight measures of 10 oranges. But in the case where you can let accuracy, you can sacrifice accuracy a little bit to get great precision, then if you've got 50 measures of 11, then at least you're pretty certain that nobody stole one of those oranges. And you had the same number of oranges the whole time, even if you're not really sure how many oranges that was. So I hope that helps.
Great analogy. Thank you. Okay, next question here. This is one that I saw come up in a couple different places. So say that you want to contribute to science, but you're not 100% sure that your data is good enough. You don't want to accidentally pollute a light curve, right? How do you judge how good your data is and if you should submit it?
Yeah, that's a great question. It's the right question too. And you know, really the easy answer is look at your data compared to other people. As a matter of fact, the first things I would go measure are things that a lot of people have measured, you know, variable stars with lots of measurements already. Or what's also recommended is go measure comp stars. Go to one of these AAVSO variable star fields where it's got 5 or 8 or 10 comparison stars noted, and treat one of those as a variable and measure that comp star as the quote variable and see how your measurement compares to the real number for the comp star. They won't be exact. You might get 11 oranges. But you know, if you're within, gosh, 5/100ths, so instead of 11.0, you're 11.05, I think you're doing really well. Ken, what would you add to that?
Walt, I'm a chemist, Walt, and measuring anything, Typically, if you're in the range of a few percent difference between you and everybody else, that's a reasonably good measurement consistency. Getting to 0.1% is really difficult to do in measurement science. And if you're approaching 10%, that's still reasonably acceptable, but something that should just make you think twice. Is there some reason I should go back and check my data just a little more? I should do that. So 1% is a nice range. 0.1% is difficult to do, and 10% is pushing things, and you should probably look at your data again.
And to put that in magnitude terms, I would call 1% to be something
It's
like
100.
0.01 magnitudes,
Yes,
right?
0.01. So 0.01 to 0.05, as you said, is 1 to 5%, and that's reasonable. That's all based on flux measurements, incidentally. You can't do percent accuracy in terms of magnitudes. It just doesn't work mathematically. And 0.1% would be 0.001, a millimag. And that's what people try to approach when they're doing exoplanets. Achieving a pixel, a transit depth of a few thousandth of a magnitude is really extremely difficult. So that should give you an idea of how good or bad your data might be.
Thanks, Ken. And one more thing I'd ask is get a hold of me or Ken or Lauren or all the other folks who do this all the time and let us take a look at your data and help you out. We're very happy to do that. Okay.
Great, thank you. Okay, so you mentioned measuring comps. We actually had a few different questions on the topic of comps. For example, Tim Stone asked when you were showing that chart up on the screen, whether comp stars have been calibrated to greater than 1/10 magnitude precision, or is that about as much as you can count on them for?
No, that is a great question, and I think I have a supporting slide. Let's see if I can. I put a few. Shoot, I didn't save that. Let me show you where you can find that.
While you're looking, Walt, typically, for example, the APAS comparison stars have a precision, a standard deviation of about 0.01 to 0.04 magnitudes. So that should give you an idea of how good or bad your magnitudes are. It's very unusual to get magnitudes measured with an accuracy of, again, a few thousandths of a magnitude or a millimag. So a few hundredths is a reasonable expectation for most standard deviations.
Yeah, and so here's how you would go find out these numbers. Now if you're using VPhot, less V photometry, some of these systems, they go get them for you. Very powerful. But here's how you find them if you're not using that software and if you just would like to know them and it's good information. You can plot your Finder chart and go to photometry table for this chart. In this case, I'll open link in another tab so that you can see the table separately. And here it is. So this is the comp star label. So 7.9 magnitude star, and so it's this one here. This is the AAVSO designation for that star. Here's its right ascension declination. Here's its V magnitude to 3 significant figures, but then this is the error that we believe, so it's plus or minus 0.059. This is the B minus V, so this is the color of the star. You can also go back to this and you can tell it you want different colors. Let's see, so I've got B and IC checked. And so it's going to regenerate the star chart. And now if I go to the photometry table, it will give me the B magnitude, V magnitude, RC if it's available, IC it's available. The little superscripts tell you the source for that magnitude measurement. And so that's how you get it. And thanks for asking that question.
Well, the important things to notice on this chart, that the magnitudes are reported, in fact, to a millimag. However, if you look in the parentheses, you will notice that the errors, the standard deviations, are in the order of a few hundredths.
Yep.
0.69, for example. So that again gives you an idea of what the precision of these measurements are when Arnie Hindon put his APAS catalog together. This is typical of what you found, what he measured. It's typically measuring only 4 or 5 images in many cases to get these numbers. If you had in fact measured it 100 times, as Arlo Landau did, he was able to achieve better precision for his measurements. And again, precision is the randomness of your repeated measurements. Has in effect nothing to do with accuracy, with how close to the truth you really are.
Okay. Thanks. Lauren?
Very useful. Thanks for showing this. This actually leads right into our next question, which was from Roel Moonen, who said, if I want to estimate the IC magnitude of a target star, but there's no comparison star in the field with a known IC magnitude, say only B and V, then what should I do?
Yeah, good question. Well, 2 things is make sure that you had the right buttons clicked. There might actually be IC magnitudes, like in this case, there's a mix. Some of them, just as you say, don't have an infrared cousin scale magnitude. Some do, but you don't get these colors if you don't go back to the chart and physically ask for them. Okay, so that said, still, sometimes you don't have it, and maybe you don't have it for any of them. And that's one of the cases where you go out to the sequence team and ask them to tell them you're doing infrared work on such and such a star in your email or in your web submittal, and that you would really appreciate some infrared magnitudes for comp stars, and they will get back with you very quickly.
Okay, great. Thank you. All right. And we also had a comment which came in on the topic of comparison and check stars, and specifically dealing with atmospheric extinction. So this was from Jean Malone, who said that, there's an assumption being made that the comparison and the check stars and the target star are all close enough together on the sky that air mass is negligible. But, if that's not, then you're going to want to make sure that the color index is close to the variable. Do either of you guys have anything to add on that topic, or would you like to explain anything related to extinction?
Well, the comment is right. In a perfect world, B minus V, the B magnitude minus the V magnitude, so in this case, 8.35 minus 7.909 is 0.441. That's generally called a color index. And so the lower that number, the bluer the star is. And the higher that number, like this one, 1.5, this is a fairly reddish star. Anyhow, so in a perfect world, you would want your comp star, your check star, and your variable star to all be very close, if not identical, to the same color. We unfortunately don't live in that world, that perfect world. And so we have to do the best we can. Like I say, try to pick what you can do. You won't be able to do it exactly. There are a couple of ways that you could deal with that. One of these that I didn't mention is ensemble photometry, where you actually would choose multiple comparison stars and instead of just a single comparison star, and that helps blend colors and blend other inaccuracies in the catalogs, and so that's a very helpful tool. But the other piece of your question or your comment too is correct, that the distance between your stars is important. And so if your stars are separated by 2 degrees, say, and they're also low on the horizon, then red stars are going to appear brighter than blue stars at the same altitude. And So when they're at different altitudes and different colors, you really are introducing some inaccuracy in your data. The general rule of thumb, though, is that for the kind of CCD and CMOS work that we do with typical telescopes, if stars are in the same field and the field is, 30 minutes square, for instance, you're going to be fine. Stay above 30 degrees altitude. That's as you get below 30 degrees, you start getting substantially larger impact of the thickness of the atmosphere on your measurements. And special care really has to be taken for DSLR photometry, because very often, and Barbara mentions this in her talk, very often you might be taking pictures of stuff that's 1-2 degrees away. You have the huge camera fields. And in that case, one of the things you can be sure and do is at least make sure that you're shooting up towards zenith, and don't even go to 30 degrees altitude if you can help it when you're doing that. So there's lots more things you can do. You can actually take extinction into account in your calculations. A lot more work, but it would really be the right thing to do in a case like that. Ken?
Yeah, I think the two interesting groups of people who have issues, most people probably have field of views that are, as you said, less than a degree or less than a half a degree. And the corrections for extinction in those small fields are typically less than any reasonable standard deviation and any reasonable precision, inaccurate, and uncertainty you're going to have. The two groups that unfortunately don't meet that criteria, as you said, are the people who have DSLR cameras and are using a lens, a camera lens. Their field of view may be 10 degrees. And in those cases, extinction should be corrected. And unfortunately, they're generally less experienced and less likely to do that. The other place where it's beginning to have issues is with some of these new CMOS cameras we have now. They have humongous fields of view. And again, you begin to get more critically into points where they should again be doing corrections for extinction, but again, may not have the experience to do that yet.
Yeah.
Some software does corrections like this. Pierre's Lev Photometry, for example, does that. And TA in VFOT does also do that. So if they look, they can correct for it. If they have a very small field, a half a degree, certainly, it's not worth worrying about.
Yeah, and I'd go on to say, if you're new to photometry, just stay away from it. You use stars that are close to each other. Don't get into an area where that's going to be a concern. It's more work than you need. You don't have to go there. Maybe go there down the line as you get more experienced and are interested in something particular that you want to do.
Sure, I'd ask all these members out there who have some experience to put a little more effort into it. It's not that difficult to do, and it will give you more accurate data.
Okay, thank you. Thank you, both of you. So I think that actually you answered a question that was in the queue waiting about ensemble photometry in the process of answering that one. So that's great. To the people who were asking about ensemble photometry, if there's anything that's still a question mark in your head, feel free to resubmit that question, but I'm going to mark that closed right now.
Lauren, I could add one thing. There are many people on, I noticed, who took the last VFOT course that I did last October. And I'm a big fan of ensemble photometry. It isn't something that improves precision, repeatability, but it does improve, I'll use the word consistency. And that's a little different than accuracy in the sense that it means your data is consistent with everybody else's. So you're getting the same magnitude number. It may, unfortunately, for a variety of reasons, not be truly the most accurate number. That could be off for another reason. The color of the target is typically what's important there. So I'm a fan of that because it makes it more consistent. And there's often a complaint on our database, our light curve generator, that there's a lot of scatter in our data. And if people used multiple comparison stars, that amount of scatter would almost certainly shrink.
Okay, yeah, good point. And
Can I add one more little bit to that too? Is
go ahead.
if you're using ensemble photometry, be sure you still use a check star.
Yes.
That's how you can still go back in 5 years when they found out that one of those comp stars, the magnitude was off by half a magnitude. It was really bad, and they need to kind of correct everything. They can use that check star just in the same way they would use correcting it via a single comp star. So the check is still very important. You could argue maybe the check is more important in ensemble photometry.
In fact, I would agree with that, Walt. And in fact, the check star is the one place where you can confirm one way or the other how accurate your data is. Because ideally, you would get the known magnitude for your check star after your processing. If you don't, that's a reason to ask what's going on, because perhaps my target star is also not very accurate.
Great point. Thank you. And so acknowledging that ensemble photometry is the best way to go in terms of improving your precision. There is a question here, which was commenting on the demonstration of VPhoto showing a single comp star. If you were to do it that way, say as you're learning, how do you choose the proper single comp star from the array that you have available?
Yeah, I still do a lot of single comp star photometry. I don't disagree with the ensemble has big advantages. Me personally, I like the fact that they can come back later and find out that that comp star was off by a 10th magnitude and easily add a 10th magnitude to my measurement. You can argue that the check star allows you that too, but if you use a check and a single comp, now you've got two measurements that you can look at. It's a debate that many very experienced photometrists still discuss. There's no perfect answer. I would certainly only do single comp star for some period of time as a new person doing the work. And to choose that comp star, the guidelines are try to use, I brought it back down, try to pick one whose color is similar to your variable star. Well, okay, what does that even mean, right? Because we don't know what the color of the variable star is. And I would say, well, yeah, maybe you do. If it is like V838 Mon that I showed you on VPhoto, that's a very red star. And we know that from lots of other things. You know that just from looking at the light curves and the measurements. And so that's one of those rare cases where I use a comparison star that's fairly red as well. Something like this. Now this isn't that star. This isn't that field.
Well, just a point of correction. In fact, the ensembles actually improve the consistency, the accuracy, not precision. And in fact, it slightly degrades precision because of propagation of errors. So one or two very good comps will actually give you the best precision. And that becomes very important if you're really only interested in very precise data in terms of a time frame. You want to know that it's bouncing with this frequency. It's really important to have good precision, good repeatability, more so than anything else. So those are definitely two different things and have two different places of use.
Yep. Thanks, Ken. Again, with regard to choosing the best comp star, then in the rare cases where it's quite red and the AAVSO actually does give you a fairly red comparison star, then you're free to use that one. You won't find a lot of red comparison stars in the AVSO database, though, because red stars are typically variable. And so the assumption is usually that a red star has some variability, and they take a lot of pains to see if this one in particular is quite steady. Blue stars, cataclysmic variables tend to be quite blue. Oftentimes their B minus V is down around 0 and minus 0.1, minus 0.2, quite blue. In that case, it's very rare to have a comp star with a magnitude with a color that's that blue. There aren't that many stars out there that are that blue, and so that's part of it too. There aren't any in the field, but in that case, you would try to, if you can, try to use the ones with a little bit of a little bit lower color index. For an awful lot of stars, they're this color range of about, say, 0.4 to 0.9 or 1 fits, and they're an appropriate comp star. It's really a tough question that we could spend too much time on, because now you get into the fact that maybe you do want to use this nice one with this little bit bluer color, but it's way off in the corner of your frame. Well, that would tell you not to use it, because that's where, even if you do great flat fielding to get rid of vignetting, it's still liable to not be quite as good. And so in that case, you might use this star that's closer, even if the color's not as good. And then one last comment on this complex topic is, if your variable in this case, let's say it's running about 10th magnitude, then you would generally want to use comps and checks within a magnitude or two above. My practice is to use a comp star that's brighter. If it's about 10th magnitude variable, then I'm probably going to use 9.8 or 9.4 as my comparison star. And then I might use one of these as my check stars. I do that because the brighter comparison star has better signal to noise, has a little bit lower error in that regard. And but I'm probably not going to choose this star, because I'm extrapolating farther, all the way from 8th magnitude to 10th magnitude, and so extrapolation is a little bit a source of error. So it's a very complex topic where you can't give you an exact answer, and use your judgment, talk with other folks, kind of get a feel for it as you go.
Yeah, Walt, it does become a subjective choice in many cases. However, because the way the calculation works, if in fact you picked a color that's exactly the same as the target for the comp star, then there is in fact no need to transform, because
Right.
correction becomes 0.
Yeah, very, very good. Very true. Thanks.
Okay,
Lauren?
thank you. So we still have a few more questions on comp stars, but we've also
Okay.
got some interesting questions waiting on the topic of, people who are setting up their own rigs. So I think we're going to take a intermission from comps and go to some of these other questions.
Okay.
Starting with someone who's curious about light pollution and its effects on ability to do photometry. Basically, how dark does your sky have to be if you want to do this?
Yeah, that's a really good question. The answer is you can do great photometry from the middle of a city.
Yep.
You may not be able to do great photometry on that 20th magnitude star that you'd like to do, that you'd really need to be out in the middle of the country on top of a mountain with a 300-inch telescope. You might not be able to do that one. But there are a lot of relatively bright stars where you can still do terrific photometry from city lights. And as a matter of fact, there are a lot of bright stars where we could really use more help. Now, that said, if you can go out where it's darker, that's great. You'll be able to work fainter, or on the same stars. Reduced sky brightness means less noise in your images and better measurements. And but I wouldn't let the fact that you don't have a great dark site keep you from helping, because there's still very much you can do.
Well, just as an example, I live 20 miles west of Boston, and I can probably see 3rd magnitude stars, but not much fainter with my naked eye.
Yeah.
But with my CCD camera, and I have both an 8-inch telescope and a 12.5-inch telescope, I can regularly get 15th magnitude stars with no problem. That means good precision. and I can see 17th magnitude stars with a little bit of effort, a little longer exposure. So obviously, if you're in the middle of Boston or New York City, then you're really going to be stuck with brighter stars. But even some of those, like Betelgeuse, are of interest to everybody. So don't let it stop you.
Great advice. Thank you. Okay. So we've had a couple questions about equipment concerns. First one here comes from John Grage, who says, my CMOS camera has a UV IR window on it. Is this acceptable?
It is. It absolutely is. It just means that you won't be able to do UV photometry and you won't be able to do I band photometry, but you can do unfiltered. In the case, for instance, of cataclysmic variables, where you're just trying to get time behavior, and so you can do unfiltered across the visible light spectrum, or you can do BVR filters, and that will work terrific.
Thanks. And we've also got a couple different people who are curious about choosing telescope, camera, and mount with the goal in mind of doing photometry. Do you have any advice on how you pick out your fundamental equipment? Like what focal ratio is ideal, and what's your minimum aperture, that kind of thing?
I could certainly say a few thoughts, but gosh, that is a very tough topic to say anything.
I'll offer one thing, Walt.
Ken, go ahead.
In fact, Josh Hopsh made a comment in the Q&A session. Put most of your money into the mount. It is the most important piece of hardware. The telescopes are secondary to that. And as I said, I have my first telescope was an LXD 55 Meade Schmidt Newtonian 8-inch f4. I still have that telescope, and it's one that sits on a Paramount. It cost $150 probably, and my Paramount cost a heck of a lot more than that. But I still use it, and it gets almost as good a result as my more expensive CDK 12.5-inch. So put most of your money into your mount. In terms of cameras, for better or for worse, you're probably going to be stuck with a CMOS camera. I shouldn't have used the word stuck with it, but you can't buy CCDs easily anymore, and certainly not in a reasonable price range. So you're going to be buying a CMOS camera. They're getting less expensive, even the QHY 600, for example, with a large field of view and a native 16-bit processor is what people are moving to. It is sometimes unfortunate that some of these cameras have enormously large megabyte size in terms of image size, 50 and 60 megabytes per image, which really make it difficult to upload images if you want to send them to VFOT, for example. So those are some comments from me on mount first. Telescope really based on how much you have to afford after you've bought a nice mount. And then a CMOS camera is what you're going to get. And again, price is really, how much money you have is really going to determine this. I would only offer a personal pet peeve. Some people, specifically people who are interested in astroimaging, like big fields of view. I think the sweet spot for photometry is a half a degree, 30 arc minutes. If so, that'll probably be slightly less expensive camera. The 268 version instead of the 600 version is a clone of that, an APS-C instead of full-size camera. So those are my comments.
Yeah, Ken, listening to you, the one other thing I was thinking we should add is, boy, if you are someone who takes astrophotography work now, you've got your rig. Start with what you have before you spend any money. You can do a lot of great stuff without having to make a big investment. And the equipment that you're already using for astrophotography is almost certainly capable of contributing photometry as well.
And just as a reference point, even though it has changed in the last few years because we got donations of telescopes, the AAVS telescopes historically, the Bright Star monitors, were 70 millimeter refractors.
Yeah.
So you don't need much to do good photometry. They may have to be brighter stars than the real faint stars, but there's nothing wrong with that.
Yeah, Barbara Harris's DSLR video she talks about using a DSLR on a stand to do bright star photometry. There you go. She has camera and a camera lens sitting alongside her 16-inch Schmidt Cassegrain on a very nice mount in a dome. So a lot of opportunity even with modest equipment.
Absolutely. Thank you. And just tangentially related. So, you know, if you're picking out a camera because you don't have one already, what pixel scale should you be targeting in as much as you can control that? Is there an ideal?
Well, a lot of things depend on that. You know, with the smaller pixels that they have in the CMOS cameras, me personally, I tend to be more oversampled than I ever used to be. My local site has average seeing when it's good. And so I consider 2.5 arc second full with half max seeing a pretty decent night. And my camera, I use a pixelation of about half an arc second per pixel. And so that's oversampled. And yet that works quite well. I suppose an optimum spot might be 1 arc second per pixel, which you could get to with binning.
Mm-hmm.
In fact, Walt, Josh Hopsch, for example, has a QHY 600 in his scope down in Chile.
Yeah.
He's on board today too. I believe Josh bins 3x3 with his QHY 600. It helps make the image size a lot smaller. And because the pixels are so small, even though he has great seeing in Chile, he actually said 4x4 is what he uses. Thank you, Josh. So you're pretty much stuck to a certain extent with getting small pixels nowadays in your CMOS cameras. So binning is the reasonable thing to try to match your seeing.
With all the caveats of making sure that you don't fall into the traps of binning where you're saturating individual pixels and you miss it in your super pixel.
Yes, that's something you do need to keep an eye on. Yes.
Yeah. So.
And speaking of binning, we had a quick question come in about just wondering if CMOS cameras is hardware and software binning equivalent?
You know, there's actually some discussion about that. Some of the binning that goes on in these cameras is opaque. The hardware binning, the on-camera binning. The belief is that hardware binning and after the fact software binning should be exactly the same. I don't know that's always the case, and I actually have the question myself I'd like an answer to. Ken, do you know more?
My understanding is, in fact, that all the CMOS cameras, in fact, have individual pixels, and you only are doing software binning. However, you can do that within your software to make it transparent. You don't know, and you actually are. Yet the final result is binned by software, but 2x2, for example. But I think in reality, each pixel is read out individually and recorded individually.
Yeah, and actually it brings up a really good point too, because I think the terms get a little bit fuzzy there. When I say hardware binning, it's not exactly the hardware binning that Ken is talking about. You know, what hardware binning used to be is on a CCD chip. Just like Ken is saying, they would not read out every individual pixel. They changed their readout mode, so they would read out 4 pixels at a time. A super pixel became 1 pixel. But just as Ken is saying, CMOS doesn't do that. Every pixel is read individually, no matter the binning. And then you can still combine that on camera and in camera. And I have a tendency still to call that hardware binning just because it's coming out of your camera already binned. But that's a little bit of a fuzzy term there. And I really don't know if they're on camera CMOS or in camera CMOS binning is truly equivalent to after the fact binning in your own software. I don't know.
All right, thank you. Changing topics a little bit right now. We had a number of questions come in on filters. This first one's from Augustin Godino, who asks if the Batter Bessel type filters are equivalent to Johnson Cousins type filters.
Yeah, that's a great question. I almost included that in here and I took it back out. The answer is yes, they're equivalent. This is another place, honestly, where the nomenclature is fuzzy and or being poorly implemented. Johnson Cousins is a set of band passes, a defined filter response. Actually full system response. So your telescope, your camera, any focal reducers, all of that. It's a certain bandwidth, and when they did their work, they used colored glass to get that bandpass, and then they said, okay, this is it. Well, there were some issues. The glasses that they used, the coatings that they used had problems. They weren't available at some point. Bessel came in, I don't remember when. Maybe it was the 80s. Maybe it was before that. He came in and he, what I think is more properly called, set up a new prescription for Johnson Cousins bandpass, and it's the Bessel prescription. And what that is actually is he changed the kinds of colored glass and the coatings and that kind of thing to emulate very closely the Johnson Cousins bandpasses. And so they're often called Bessel filters, but in my view, they're Bessel prescription of Johnson Cousin bandpass.
I agree with that, Walt. Yeah.
Yeah, and of course the funny thing about that now is the filters that we're actually using aren't the Bessel prescription filters either anymore. If you're buying interference filters from, gosh, Astrodron, Chroma, Botter, several different companies, those are interference filters. They don't use colored glass at all anymore. And so they're not using the Bessel prescription of this kind of glass and this kind of, they're not doing that anymore either, but they're still calling them Bessel filters. And yeah, so in my view, this does not reflect the thinking of the AVSO as an organization. In my view, I don't think they're using the right terminology. But yes, if you buy something that calls itself a Bessel filter, then you're getting Johnson Cousins bandpass.
Okay.
In fact, it turns out this is a common question, especially as it relates to transformation. My filters, whose filters are good enough?
Yeah.
It turns out, and Arnie has promised to give us a little tome on this in the near future, but there has been data generated and produced in the webpage. Most of, for example, Beta, Optolong, in fact, what's the other one who comes to our meetings, Walt?
Chroma.
Chroma. All, in fact, have, in general, don't quote me to 100% accuracy, but have reasonable transformation coefficients. And that means typically, instead of having a color coefficient of 1, which is optimum, you may have 1.1 or 1.25. The only times when you really get significantly different from that in most cases is if you're using an RGB camera, a tricolor camera. And those filters do not necessarily conform as well to the photometric filters. But in fact, even then, many people are using tricolor cameras and getting good photometry. Their coefficient may be a little larger than the 125% that I talked about, but still reasonably acceptable. And the bottom line is that they give reasonable results. That's really the bottom line.
Yeah, just real quick, this is one of my backup slides. This is on the top graph, the B, V, and R spectral response for Johnson-Cousins bandpass. This is RGB for a DSLR. And while yes, that is R, that's G, that's B, sure, that's great. The issue is just that it matches up pretty well, G and V. R and B, on the other hand, don't match up quite as well. And another subtlety, if you're working on stars that have huge H alpha emission, then you really can't transform the R from an RGB camera into the R of a Cousins R, because it's way out. It's not covered in their R, and these scales aren't exactly right, but anyhow, that's a little more detail on some of the issues of band passes lining up and being transformable.
Okay, thank you. All right, so at this point, I'm going to take a quick pause because honestly, normally this is where our Q&A starts winding down, but this is such a popular topic. We still have a very long queue. I want to be respectful of both of your time and ask, at what point would you like for us to kind of wrap things up here? Do you have time for, say, another 30 minutes of Q&A, or should we wind down sooner than that?
I'm okay. I can go.
Okay.
Okay.
An hour is probably pushing it, but anyway.
Gotcha. Okay. Okay, thank you. Well, in that case, we do have a couple of questions related to what you were just talking about with filters. This one from Aries Aquaria is asking about whether it's okay to mix filters from different manufacturers.
Yeah, that's another great question. The answer is yes, with an asterisk. Matter of fact, we can talk about a particular case. Astrodon was a company that made filters for years, just really fantastic filters to kind of change the world of amateur photometry. And but Astrodon filters are no longer in production. And so a lot of people, me included, sometimes have partial sets and would like to get something else. And the answer is yes, you can mix them, but with the caveat that it helps a lot if the thickness of the substrate is the same. And so, for instance, an Astrodon filter is a 3mm glass substrate that they put the interference layers on. While some companies, maybe I shouldn't mention companies in particular, but some companies now use only a 2mm substrate, which is fine. The only difference, though, is that now when you focus going from one filter to the other filter, you've got that extra millimeter of glass that changes your best focus point by, round numbers of millimeter. And so you end up with a little bit more worry with offsets as you change from one filter to the other. And so if you're mixing, the ideal thing to do would at least stay with substrates that are the same thickness to minimize that issue.
Walt, the other little wrinkle with respect to different thicknesses is I believe the ZWO filter wheel is a little bit less thick. And we had to actually mill the filter wheel a little bit on the AVSOnet to fit in the thicker filters.
Really?
So
wow.
keep that in mind. But Ari is the one who asked this question. My opinion is it really doesn't matter if you use one versus the other, except for this focusing issue, because you're getting an individual transformation coefficient for that filter. And it's going to be different for the R, the G, and the B, or the BVRI. So who cares to a certain extent?
And with all this discussion about transformation, I'd want to emphasize to folks who are starting out, don't start there. Don't start worrying about transformation in your first work. It's something that's very powerful, very important down the road, but you can do an awful lot of work either unfiltered or with the straight V filter, untransformed. It's better if you transform it, but your data is still valuable, especially as you learn if it's not transformed.
In fact, at least 90% of our data in the database is not transformed.
Yep. Thanks. Good point.
Yeah, great point. Yeah, definitely not the place to start out. And it's also worth mentioning that, you can take the stuff that you've learned from this webinar, go get your start in photometry, keep it simple. And then if transformation is something that you're interested in, we actually are going to have a webinar later in this series, which will be focused just on transformation and how to do that correctly. That will be our May webinar. So you've got a few months there to get some experience under your belt before you start considering it. Okay, let's see. So we had a couple of questions that were still related to filters, but now talking kind of about the science cases and the astrophysical interest. So first of all, actually another one from Ari, who says that right now he has a B, V, and R. He's wondering about whether he should get U and I filters. Like, what's the science reason? What sort of interesting stuff can you observe with those?
Yeah, well, that's a great question, and if you don't mind, I'm gonna use Arnie Hendon's often response. It depends. Um, there are science options where those are important, and places where they're not important at all. And actually, let's start with the U filter, the U photometry. Some of the places where that's most important, for example, would be cataclysmic variables, because the U ultraviolet is the higher energy things going on in the systems, and cataclysmic variables typically very blue, typically a lot of things going on in ultraviolet. Um, At the same time, ultraviolet photometry is very hard to do well. There's a couple of reasons for that. One of the reasons is that often the amount of light that's transmitted through your system, especially if you have some glass in your system, is the ultraviolet amount of light coming through is going to be pretty low. If your star isn't quite blue, there's not much ultraviolet there anyhow, even to get. And then the last part, and this is a real killer, is that moisture in the atmosphere, that in a perfectly clear sky, moisture that you don't see, can impact your ultraviolet photometry. And it's probably out there somewhere on the web. It was a all sky shot from Cerro Tololo, or one of the amazing top of the mountain observatories, where they showed the night sky on a perfectly clear night. They showed an all sky video of it in ultraviolet. And it was just shocking to see how much, quote, haze went through on this perfectly clear night. And that's Cerro Tololo on top of the mountain. Here in Houston, for instance, we don't stand much chance, I think. It's too moist. So I think you have, for ultraviolet, you really would want to be in a drier environment with some altitude to have a chance to do good work. But let's get back to what your real question was. I said ultraviolet's hard, maybe too hard for a lot of folks in their position. In the infrared world, places where that's important include young stellar objects. Miras are extremely bright in infrared, and let's see. Places where they're less helpful would also include, say, RR Lyraes and that kind of thing, because the amplitude of the variation for an RR Lyrae or a Delta Scuti or a Cepheid is much lower in R and I than it is in B and V. So the work for those kinds of stars is typically B and V, because you get that great amplitude and you can see more. Ken, where else is I? particularly indicated.
I mean, cool young stars is clearly one of the areas. One I typically would recommend starting with B and V. Well, clearly V first.
Yeah.
B
Yep.
and V, and I skip over the R in many cases and think the I is a better one to get. I think one of the other things that Ari asked was, what about mixing Sloan and Johnson Cousins? There's a basic historical rationale for saying stick with Johnson Cousins because it's what our database has in it mainly. But if you don't follow or conform to that desire, perhaps, there's really no reason not to mix Sloan and Johnson Cousins. And in fact, I think Arnie's latest iteration or recommendation, if you will, was getting BV and GRI, Sloan GRI, because in fact, that's what he used in the APAS telescopes.
Yeah.
Because you can do different transformation. Don't get confused by the words, but you can transform the data between the systems. So even if you don't have a magnitude, in fact, Pierre's Lev photometry does this very nicely. Good hint for you, Pierre, again. So it's reasonable to pick what you want, and your data will be useful. Again, remember that historically Johnson Cousins is what's in our database most, but most professionals, in fact, use the Sloan system, and they're going to be reviewing our data.
And let me emphasize one other thing that Ken mentioned there too is a really good point. The when you talk about BVRI, whether that's Johnson Cousins or its kind of equivalent in the Sloan world, yeah, R is the one actually that people would leave out. If you can only get 3, you would get BV and I, for instance. And one of the reasons for that is because when you're looking at colors and how colors in a star change, which they often do in different types of variable stars, the B minus V, that color index, is something that you can watch move. V minus R, that color index is rather small and maybe not as informative. And so rather than V minus R, professionals often are more interested in V minus I. They skip R entirely. And so that would be why you'd have B, V, and I to do that kind of work. Now I will say that I bought a BVI data set and then wished I had bought the R and finally went back and bought an R. So, it's nice to have the capability so that you can use what you like for the particular situation.
Okay. Good to know. Thank you. And I think that actually answers some of these other questions that we had here about Johnson Cousins versus Sloan filters. Perhaps the only one which should be addressed separately is just say that you don't own any photometric filters at all. You want to make an investment, but only in one filter set. Which one is best to start out with right now? Should you go ahead and invest in just Sloan filters, or would you recommend always having that V and B filter at least?
Yeah, tough one.
Oh, Walt, it's not tough. If you want to get one filter, because that's all you can afford, you get a V, a Johnson's V.
Yeah.
That compares to the visual, which is really what you want to compare.
Okay. Great.
But I would say if you're building a set, I understand Arnie's point on B minus V, Johnson Cousins, and then maybe G prime, R prime, I prime. Personally, I'm still. I like the fact that if I do everything Johnson Cousins, I'm able to compare with the last 50 years of Johnson Cousins data. And so I haven't made the jump to Sloan very much yet.
I have both sets in one of my filter wheels, Johnson and because again, if you only have 5 spaces in your filter wheel, then you're going to have both.
Yep.
Okay, thank you. Now, pivoting a little bit here, we had a couple interesting questions specific to doing photometry of supernovae. So first, question from Tatsuji Tanaka, who says supernovae, they typically appear very close to or inside the parent galaxy. How do you deal with the uneven background there?
Yeah, yeah, great question. I worked with a professional on some of this once, and the way he actually did it was we did all our all our imaging of the supernova as it happened over time, and then 2 years later made sure to come back and re-image just the galaxy with the exact same equipment once the supernova had faded, so he could subtract the galaxy. And but it's a hard question. It at least makes it harder to compare with other people and to get absolute numbers. For your own numbers, you can just take the fact that you've got this background galaxy and you squeeze your aperture, and then you keep that aperture the same and your sky annulus the same for all of your work, so that you can say all of your work was at least consistent or precise, even if there were the accuracy issues that were hard to figure out.
Mhm. Okay, thank you. Our next question here is from Roger Menard, who is curious about finding comparison stars for newly discovered supernovae. These are often down in the magnitude 15 or 16 range. What do you do about comparison stars for new variable stat faint?
Well, the faintness really isn't a problem. I have asked for sequences or for additional comparisons for stars down 17, 18, 19th magnitude a number of times. I think really the only issue is that you have just a little bit of patience, if your data can stand it, to wait a day or two for them to get that work done for you. The exception would be if you are doing a newly discovered supernova, or you just found one and you need a brightness. In that case, you've got to have a comp star right away. Couple of opportunities. One is APAS, which was Arnie Hendon's AAVSO photometric catalog work. And that's available on the AVSO website. It's very dense, lots of magnitudes. I think his
Only goes to 15, Walt. Only goes down to 15.
okay. Yeah, I was thinking it actually went a little fainter than that, but either way, for a supernova or photometry on something that's maybe 17th magnitude, you can use a 15th magnitude star to do that photometry. I doubt your 15th magnitude star is overexposed if you have a regular amateur equipment.
Yeah.
And if it is because you've taken long exposures, then stack shorter ones instead to be able to deal with that. There are other catalogs out there. The Atlas catalog is a derivative of APAS and some other work where the Atlas program on Mauna Kea has re-reduced a lot of Arnie's work and added some additional work to generate comp stars. That's very well thought of too. So those would probably be my go-tos in a emergency in a short time situation.
Okay, thank you. And so going the other way with target star brightness, we had a question here from Luis Serra, who was curious about what do you do when your target star is much brighter than all of the available comp stars?
That would be AB Aragi. Yeah, we are very actively working a program right now. Maybe it's the one that you're talking about. In our case, AB Aragi is a very bright young stellar object, and the nearest comp star of some brightness is 3 magnitudes fainter, give or take. And so in that instance, the best thing to do, you would like your comp star to have a signal to noise of 100. You'd like it to have more than that if you could, but certainly 100 would be good. And so take shorter exposures or take multiple exposures and stack them First calibrate them, then stack them. Being sure that you go to, say, a floating point in your fits, so you don't so that you actually get the benefit of your stacking. And you can sum your exposures or you can average them. Honestly, it's the exact same thing as long as you're using floating point. Averaging and summing are the same. You get the same answers, the same photometry, but that way you can build up the signal to noise on your comp star and your check star, and you end up with amazing signal to noise on that bright variable star. But that's okay. Now you've got enough signal to noise in your comp and your check that you can do very good photometry.
Great.
Yeah, I think, well, most people are going to do that. Most of our amateurs are going to do that. One of the classic things is to go back to what the professionals do and do all sky photometry. It's what our PEP folks do. Their comp and their target are in different fields of view. But at that point, you must do all of the corrections for extinction and color transformation. So it's not something most of us are going to do, but that would be one ideal way of doing it.
Yeah.
Okay, thanks. And you mentioned you want at least a signal to noise ratio of 100 in those comp stars. That leads into our next question, which is just about what signal to noise ratio should you be targeting in your target star when you're doing photometry?
Yeah, back to that it depends answer. Generally, if you are working a star that you're not doing a time series, you're not looking for time behavior, then you'd certainly like to have a signal to noise of 100 or better across your check, your comp, and your target. And you can certainly go much higher than that too, as long as you don't get into saturation. That can just improve your data, reduce the noise. The caveat, though, is if you are doing time series data for instance, cataclysmic variables, supernovae, that kind of thing, where you're trying to get the highest cadence that you can so that you can get the best time resolution that you can. In that case, Dr. Joe Patterson is an astronomer at Columbia University, and he is the shepherd of the Center for Backyard Astrophysics. And so he has been looking at amateur data, time series, to try to dig out time frequency data in star behavior. And his recommendation is the best balance of high cadence and good enough signal to noise would be to give a signal to noise of about 50, and that you can still get pretty good photometry, good enough to be able to get good signal and the highest possible cadence. Now, I will say that he'll bend that, and depending on the particular star, he even signal to noise as low as 20 or 30 can be useful if what's happening in that particular star is fairly decent amplitude, so that it sticks out. And so that's a fuzzy answer to the question.
Well, just as a mathematical reference point, that SNR of 100 gives you a precision of 0.01. So you 0.01 magnitude, which we've said, gee, that's good, 1%. If you went to 1,000, which weren't saturated, that would be 0.001, a millimag precision. If you went to 50, that's 0.02. Well, is 2% not good enough for you? If you went to 10, that would be 0.1. That would be 10%. Is 10% precision in your measurement not good enough? In fact, in reality, an SNR of 3 is what you can just detect visually on an image. So 3 to 5 is something I can just see it. Do I want to report it because nobody else in the world has shown what the magnitude is for this star, this new supernova that hasn't grown in magnitude yet? So that's the thing to keep in mind if you want to have a mathematical reference point for how good or bad it is.
Thanks, Kit.
Okay, so just for reference, we have about 8 minutes left in the Q&A. And our next question here is about stacking algorithms. Is there a preference for whether you use in terms of statistical algorithm, a percentile cut, a sigma clip, a Winsorized sigma clip? You know, what's preferred?
Yeah, that's a great question. My answer would be don't use any of those. Um, and that's not necessarily the correct answer either. You know, what those algorithms are doing is they are cutting off outliers. And that's very helpful for you know, if you have cosmic rays, that kind of thing, you know, there's certainly value in that. Um, I haven't found that those impact it very much, and that improving it doesn't improve my photometry enough. You know, there's some risk that you are mm, playing with the data, and pushing your photometry a little bit, not on purpose, of course. Um, Maybe what I should say is I should say pass, and that would be a question best answered by some of the pros who have been doing photometry much longer. Just because I think there are some gotchas there, and so I really stay away from it myself. But Ken, how about
comment, Walt, is, you know, if
what's
you
that?
are, if my comment is, if you are trying to get rid of outliers purely to get the smallest precision value, 0.01, 0.005, that is not a valid reason for using any of these cut procedures. So use it with caution. And again, if it's, you know, in VPhoto, there are some red highlighting associated with individual comps. And the redder it is, the further it is from the average of all of the target magnitudes. So that tool gives you an idea of, gee, is that just a little too poor a value from my comp and I should get rid of that comp? It gets down to be a judgment call based on how clearly you think it truly is an outlier, and that has its own statistical analysis to determine that. So I think your caution is reasonable. And I think we've concluded that, you know, use an average, use one standard deviation as a cutoff in some cases, or two standard deviations, but you don't really need to go to these other special clipping tools unless you have a strong reason for doing it.
Well, and particularly with stacking, it does bring up just kind of the more basic, broader issue that a lot of the things you learned to do and are so successful with the amazing astrophotography people do, you can't do that. Please don't do that. You really, this is data, and you know, you have to calibrate properly, and then only a little bit more might be acceptable, and some things not acceptable at all. And that's a broader discussion, maybe not to get into at this point. But you do have to work with your data appropriately. There are just constraints of what you can get away with and what you shouldn't be doing when you're doing photometry. And the answer is it makes it easier for you. All those cool things you did with astrophotography to make images look great, well, they're not allowed, and you're asked not to do it for photometry. So
Okay. So I think we have time for two more questions here. First off, oh, where'd it go in the queue? Yes. Okay, so this question comes from David Gay, who's curious about the method of defocusing your telescope slightly in order to improve the signal to noise ratio. Do you have any recommendations related to like how much should you defocus? Does this really work? That kind of thing.
it does work. It can be helpful. You can't do it a whole lot, but Ken, maybe you have more experience with that.
Well, two observations. If you get to a donut, then you've gone too
Yeah,
far, because
right.
then plate solving is difficult.
Yeah.
You know, we use an offset that probably, something like changing it from 2 to 3 times the full width half magnitude might be the extent of the defocusing we would use, maybe go to 4. So it's actually going to reduce your signal to noise ratio because you've spread it out over more pixels. So it'll be less strength in 1 pixel. So do a little. Go ahead, Walt. You got a question?
Well, no, I was going to say, depending on what you're doing, it can improve your signal to noise also. If you've got a super bright star, and now on a single frame, you're able to, you measure all billion photons over a larger number of pixels, that can improve it. But I would also say, what I've seen people done, what I've personally done, other folks have done, is try it. Try different levels of defocus. What Ken says is very true. At some point, if you have to plate solve to do your photometry, it's just gonna die. It's not gonna be able to manage the terribly defocused, potentially donut-shaped stars.
All right, thank you. And I think our last question here for today is going to be this one from Aaron Berner, who asked if you have any recommendations for first-time targets, good stars for someone who's inspired to go out and start shooting.
Well, one that I've done recently that I think is an interesting one is T-Tari. It is a cataclysmic variable that's quite bright, and that just happens to be one I've been working since recently. But a better answer, honestly, is to do something that others are doing. Some friends of mine who are just now getting interested in doing photometry are working SS Cygni, for instance. Since there's a lot of data, they can compare very directly with what other people are doing, and that's a really interesting system that has been watched for many years, and we're still learning. Miras are also good systems. The only curveball they throw you is that they are quite red, and so that can give you a little bit more error if you're not doing filter transformation, and maybe throw you off a little bit.
Walt, I'm asked this question many times in the classes.
Yeah.
From my point of view, short period pulsators it's just fun because literally in one evening, a couple of hours, in the cases of Delta Scooties, you get a nice light curve. Even exoplanets, even though they may be a little more difficult if you don't look at the ones that have a deep transit, you're seeing something after one night's imaging, and that really makes you enthused about what you've seen. This was fun. Wow, I got a light curve. I can see an exoplanet somewhere in the universe, in the galaxy. So that's what I usually tell them. But all of these other things have a valid reason for doing them. They give you more science, and the professionals like that.
Yeah.
I'm a glutton for punishment. I like things that give me instant response.
Well, and it's a really good point, Ken. And based on that, I throw one more out that I quite get the kick out of imaging is any kind of cataclysmic variable system that has a total eclipse. And the cataclysmic variables are almost always an interesting light curve anyhow, because they bounce around all over and they do all kinds of interesting things from minute to minute, hour to hour. But quite a few of them are tilted in the right plane so that we see this big deep eclipse. And that is just a beautiful light curve to see something bobbling along at 11th magnitude and then chase itself down to 14 or 15 and then rebound over the course of an hour or so.
Sure, all the eclipsing binaries, that you're going to see something over a couple of hour period.
Yeah.
And that's, again, it's fun. And our Lyraes generally have a period of a half a day. So again, in an evening, you're going to get a nice light curve that you.
Yeah, I'm not sure we're helping at this point, Ken. We've got 50,000. We didn't give too many specific names of stars, but maybe our Lyrae itself is a good one. It's bright. It draws a beautiful curve. I don't remember the period exactly. It was a day or so, something like that.
Yeah.
And Gosh, I can't think of any eclipsers right off the bat.
Yeah, just look on the target tool. You'll find some.
Yeah, good
Yeah.
point.
The target tool and the VFX as well could be a
Yes,
useful
yes.
place to search. You can search by variability type there, but if I remember correctly, you have to hit the more button twice in a row to
Yes.
get that option on the search form.
Yeah.
And I am not going to admit how long it took me to realize that fact. All right, those are some really great recommendations. Thank you both so much. I'm gonna let a bonus question sneak onto here because it's kind of meta. We had someone ask about the slide deck that you've created here, Walt, because it seems like a really great resource. If you'd be willing to share it, then feel free to like ping me with the link later, and I'll make sure that it ends up in the YouTube description, so that people can reference it. And of course, the video itself, all of this webinar has just been recorded and it will go up on YouTube. So regardless of whether the actual PowerPoint deck is available, you can at minimum flip through it there, to the people who are asking about that. So
Yeah, Lauren, will I just send you the slide deck and you'll put a link to it on the YouTube channel? Will that work?
so when we upload it to YouTube, we can set the description of the video. So I was saying I'd put it in the description of the video so that if someone wants to quickly access it and flip through, they can do it that way.
Yeah, I don't have a link. Could the AVSO host it? Is that what you're saying then?
Yes, we can host it.
Okay.
Yep. So in that case, if you send me a copy via
Yeah.
email, we'll host it on our site and put the link in the description.
Well, and actually, if anybody wants to shoot me an email, I'll happily send you a copy too. I hate to announce my email on YouTube and Facebook for that matter.
You can type it into the Zoom chat if you're okay with it going to the people who are here. Or you can also give people your username on the AAVSO site, and then AAVSO members can look you up and use your contact form without you giving out your email. That's another
Yeah,
option.
that'll work. I'm CWT
Okay.
in the AAVSO world.
All right, great. So if you use the membership search tool, anyone who's watching, you can look up Walt's contact form and send him an email that way. All right, so this has been a really excellent session. You know, I think this presentation was kind of the perfect beginner level introduction. I want to reinforce for those of you who are still online with us that you know, if you're brand new to photometry and your head is, you know, maybe swimming a little bit after the Q&A, not everything that we talked about here was stuff that you necessarily need to understand right when you're getting started. You know, as Walt and Ken were saying, some of this was advanced, some of it was beginner level. Just dive right in and have fun with it. And before you know it, you're going to be taking your own precision observations. And I think I'll go ahead and put up the closing slides here. And oh, yes, one other thing, because we have so many questions left in the queue today, I just wanted to mention that the AVSO, we do have a forum all about photometry where you can go and post your questions. So if you had a question that we didn't get to today, I really highly encourage you to go to our website, go to the photometry forum and post your question there, and you will very likely get some expert answers there. I dropped the link in the Zoom chat. It's aavso.org/forum/5010. That's the code for the photometry forum. All right, and let me pull up our closing slide here. Share screen. All right, so starting with our most important announcement, I would like to first extend a heartfelt thank you to both Walt and Ken for sharing their time and knowledge with us today. This was a really excellent presentation, and I think the Q&A might be the best one that we've had in a long time. So thank you both. Thank you.
Yep, our pleasure. Thank you.
Great. And before we close out, I would also like to thank again our sponsor, Boyce Astro. The Boyce Research Initiative and Education Foundation provides online astronomy education, observatory resources, and research experiences to students, student teams, and schools in order to learn how to perform observations, conduct research, and publish their results in scientific journals, like the Journal of the AAVSO. Please check out their webpage to learn more about their work. Today, I would also like to extend a special thank you to everyone who's here in the audience. You had some really great questions that helped to make today's session into a special educational resource, and I'm grateful to you for that. But even more than that, it's your participation in all of our programs which allows us to keep growing, keep educating, and keep making an impact on variable star science. So we'd just like to say thank you, each of you. We're very grateful for your support. Today's broadcast has been recorded, and if you'd like to go back and reference that recording, you can find it on our Facebook page. It should be automatically uploaded just as soon as we close the session here. Within a couple days, you can also find it on our YouTube channel, where it will join our enormous library of past educational videos, including that webinar presented by Dr. Harris that was mentioned a couple times during this session on DSLR photometry. You can find that library of educational videos on YouTube by searching for the username AAVSOHQ. If you just search AAVSO, it might not come up. Experience talking here. Now, when you log out of the webinar today, you should be automatically shown a survey. I would really appreciate it if you could fill it out. Let us know what you thought of this very first webinar of the year and what we can do better next time. All right, I believe that's it. So I'd like to close by expressing one last huge thank you to both Walt and Ken from all of us here at the AAVSO. We appreciate you and everything you do.
Thank you.
Bye-bye.
See you all next time.